So in the last session, we have seen stack corruption, and we have rebuilt the stack using different parameters, ESP, EIP, and EBP, using the special K command. Same thing we have done in the chapter 2. So we are able to reproduce the behavior in this chapter as well in live scenario. But it all depends on the nature of the corruption like we discussed. Now let's get into the next issue in the not my fault. Next issue in our bucket is high IRQL fault UserMode. We'll see what is the issue. First, let's crash it. So I'm gonna click the crash button. It is not responding right now. So it has broken into the debugger if I'm not wrong. As expected, it is broken into the debugger. As usual, we're gonna go with bang analyze -v because it's a crash. Bang analyze -v. So I'll explain what is this issue shortly. Here itself we can see returning to user mode from a system call at an IRQL greater than passive level. That particular sentence explains the problem pretty precisely. So you're returning to user mode from kernel mode. Right now you're in kernel mode, but you're trying to return to user mode at an IRQL greater than passive level. Let's try to draw the entire problem real quick. We have the address space here. We have the user mode here. And we have the kernel mode. In the process of a system call, in this case, device IO control, so we switched from kernel mode to user mode. We made a switch. We did the processing of the IRP. There's an IRP created inside the kernel mode by the IO manager to satisfy that particular request. Then we are going back. So we are done with this processing. Now we need to return back to the device IO control from user mode to kernel mode. This is the application right here, the user mode application we are dealing with. In this case, it's the not my fault. The crash is happening around here. When we are trying to return from kernel mode to user mode, after the call, the system checks for the IRQL. And if the IRQL is higher than passive level, we'll get this particular bug check. That is exactly what is written here. Returning to user mode from a system call, which is a system call in this case, device IO control, at an IRQL greater than passive level. In simple terms, in the generic operating system terms, you are trying to return to user mode or normal application running mode with an interrupt masked. Interrupt mask is on. Remember, IRQL is nothing but interrupt mask. It is masking the interrupt and returning to user mode, which means that from an operating system perspective, it doesn't make any sense. What is happening? The system has a check here to do or check whether we are doing it. And if that check is satisfied, system is crashing or bug checking. That is what is happening right here. Let's continue with the analysis. We have the address of the function call, the system call routine, and the current IRQL, the IRQL which is making the problem. The IRQL is 2, which is higher than the passive level. Passive level is IRQL 0. The system call which is under progress is device IO control, like I was mentioning. So it is all coming from the not my fault. No surprise there. I'm just doing a bang thread here to see the status of the IRP. I'm going to dumb down the IRP right here. Bang IRP. As you can see here, the IRP is completed. IRP is completed. So the IO processing is done. Someone has called IO complete IRP on that particular IRP. It is done. Now you need to return back to the user mode. That's what is happening. If you look at the call stack here real quick, the call which is crashing is K fast system call ret. Let me highlight that. KI fast system call ret. This is a call which is crashing after calling this. This is a call which is calling the KE backcheck EX. We are returning from the system call. That is what the call stack is all about. One of the things to notice here is that the driver which is responsible for this problem is not there on the stack. There are good amount of pointers to that driver, especially from the IRP. The completed IRP is pretty much on that particular driver. So that is one pointer to the myfault.sys, or that is enough indication to rename that driver or disable that driver and try to reproduce a problem. If you look at the call stack, you will not see that particular driver, although that driver could have caused this problem. This is one of those problems which the actual culprit is not there on the stack. I'm going to do an ln on this particular address, which is there in the bug check code. No surprise, it is NT device IO control. So that is the address which we got from the bug check code. Not particularly useful, just showing you. Quickly looking at the current IRQL. It is already 2 as per the bug check code. Processor 1 has the IRQL 0. I'm switching to processor 0 just to see what is the IRQL of that process. So you can always mention like this IRQL then the name of the processor. If you want to avoid switching the processor context, you can always mention IRQL then the number of the processor which you're trying to get the IRQL of or the interrupt mask of. The debugger saved IRQL I have seen not always 100% reliable, although it is the IRQL which is supposed to be relevant to our purpose, but I have seen it is getting overwritten over the collection of the dump and stuff like that. In this case, it is not showing the problem correctly. It is showing low level or passive level in this case. There is only 2 processor, so that is why IRQL 2 gave me an error, which is expected. One of the things I would like to show you is the call or how a system call is returning from the kernel mode. We're going to look at the disassembly of ntki system call exit. That is the function which is bug checking here. I just wanted to show you how the bug check is happening from that particular function call. UF, that particular function, that is how we look at the disassembly of that particular function. So it's a pretty big function, as you can see, a lot of code, because it's the single most important function when we come back from the kernel mode to user mode. So it has a lot of security implication and stuff like that. It needs to check a lot of things. Whenever we look at this kind of big functions, which has a lot of assembly code, always try to understand what you're focusing on. What is your aim? It's just like you're going to a big supermarket and a lot of things are there in the supermarket and you don't know what to buy. You always go to a specific counter and take whatever you want. That is the exact same thing we're going to do. We are interested in the IRQL here, and there could be n number of things which is there in this function we're going to ignore. Let's see if we can do that. As you can see right now in the screen, we can see get current IRQL. That is the call we are interested in. If you look a call to dword ptr ntbang import ke get current IRQL, that is something which we are interested in. What is it doing after that? It is doing an OR operation AL, AL. That is the lower bit of the accumulator or EAX register. And then based on that, it is doing a JNE to the branch, jump not equal to, which means that the return value of the previous call, if it is not 0 or any other value, it will go to this particular branching. That is what this to instruction is all about. Basically, we have an OR AL, AL. The return value of this particular call is going to be in EAX register. So all the return value is going to be in the EAX. We have seen that before. Now, we are not interested in the entire EAX. We are interested only in the lower part of the EAX because IRQL is a very small value, which is less than 32 in most of the cases. We are comparing the lower part of the EAX register, which is AL. That is the lower part of the EAX register. Now, why we are doing an OR? If this value is anything else other than 0, this operation will result in a non-zero value. If that is the case, if the result of this instruction or instruction if anything other than non-zero, this jump will satisfy. jump not equal. If it is equal, the previous operation will be 0. That is the assumption. I have to admit that these two instructions are not very intuitive, but you will see a lot of jump and comparison like this in the assembly world. It is the compiler which generates this kind of instruction. So compiler is not assuming it to be intuitive. It's not very intuitive. There are many other ways to check a value is 0 other than ORing it. There are a lot of performance reasons and stuff like that, which I don't want to get into. But in short, anything other than 0, if returned from this call, you will get to this particular branching. Now what we're going to do is we're going to go into that branch. We are going to the branch, and then here it is. Here is where the branch comes up. In the branch, I'm going to ignore a couple of instructions. First 3 instructions which are not really worth mentioning here. These are the instruction which is of interest to us. We are calling Windbg. This is from where we are getting all the values to the backcheck. This call, that is a call which gives the blue screen of death or BSOD or crash, whatever we call. This is where we are filling up the parameter. Why we are calling bugcheck? Windbg, it's a documented API you can call from your driver as well. This is like throw instruction in C++, a throw which cannot be caught, a throw which guarantee to cause blue screen of death. In fact, the handling of the bugcheck is nothing but the dump collection we have seen before. This is the call which causes the crash in Windows operating system. I don't think I have shown you this, so I just wanted to discuss that. There are so many parameters it takes, and those are the parameters which gives more information about the bug check. There are a couple of other things it is doing, like saving the context, some of the context, etc. Another interesting thing it is doing is calling CLI. Don't want to get into the details of it again, but just to give you a very quick overview, CLI is clear interrupt, which means that system cannot be interrupted while this call is in progress. It's like IRQL raising to the highest point. All the interrupts are masked at this point. There is an opposite call for that, which is set interrupt. Clear interrupt is the way of telling the CPU, hey CPU, I'm going to execute something and I don't want any disturbance whatsoever from any device. That's what this CLI is doing. It is giving the execution a very real-time nature. No interrupts at this point. That is what I wanted to show you in this particular problem we are facing. We have seen the assembly and how the bug check is getting created. That's what I wanted to show you. Again, it's a very big function, but we focused on what we need, like we discussed.